Hi, everyone. I want to start the topic of magnetic susceptibility, and this is really just intended to be a very brief introduction to the topic. We're not going to really get into a lot of the experimental details. But in general, when you think of magnetic molecules and materials, and that's synonymous with magnetism, what you're normally thinking about is that the spinning electron in a molecule material will generate a local magnetic field. And, the typical concepts that you think about with any magnetic material is that they naturally have magnetism because you have unpaired electron spins. And if they're randomly oriented, like they would be, for example, in a powdered sample, you can actually magnetize the material because you can force the very little magnets that you're basically generating in each molecule can be aligned with an external magnetic field. And when you do that, that's called magnetization, or it can be magnetized. And then the idea is the more unpaired electrons you have in your sample, the more susceptible the material will be to being magnetized. And of course, it's that word susceptible that then leads us to really thinking about magnetic susceptibility. So materials with unpaired electrons are paramagnetic, as we've discussed before, and they get attracted into an external magnetic field, whereas when you have materials that are all paired electrons, or typically what you'll find is when materials have all paired electrons, those are typically called singlet states, but those are diamagnetic, and then they're actually slightly repelled by the application of an external magnetic field. So what you do with magnetic susceptibility, and to measure it, is that you measure basically the mass of a sample in the absence and presence of the magnetic field. And then what you're kind of going to get from this is that that's going to then be proportional to the moles of unpaired electrons in your sample. And then, of course, that's going to then be proportional to the actual number of unpaired electrons per molecule or per unit of material. So the way the magnetic susceptibility balance works is it can work in two different ways, one of which you can kind of have the sort of classical type of measurement where you have a sample that's contained here, and you basically float it above a permanent magnet. And what will happen is, if the sample is paramagnetic, it'll get attracted into the magnetic field, and then that is going to then effectively weigh more as a result of that process. So the mass will appear to increase, and that's going to be a function of effectively how paramagnetic the species are, and then their actual how many paramagnetic molecules are actually in the sample itself. And then if you do this on a top loading balance, you kind of can do the opposite type of experiment. You actually have a magnet that's weighed, and the magnet that's weighed is then kind of put into the presence of a paramagnetic sample that's floating above it. And the net result of this will be is that the magnet will get attracted to the paramagnetic species, and you'll see that the magnet actually will get pulled towards the sample, and then the magnet actually will attract up and weigh less. But the important thing is that the change in mass that you measure is going to again be proportional to the number of unpaired electrons in the sample. And that's really all we care about. And then that weight change, of course, is related to chi. Chi is actually known as the magnetic susceptibility. So that magnetic susceptibility is going to be related specifically to the magnetic moment of the electrons that are present in the sample. So the idea is magnetized samples generate a magnetic field. The strength of those individual magnetic fields is mu sub s, and that is called the magnetic moment, which is typically resulting from the electron spins of the material. And then mu of S is related to chi T in this particular way, and T is temperature. And remember, chi is magnetic susceptibility, but it's 8 chi T to the 1/2 power. And then that's typically the experimental magnetic moment that's measured for a given molecule or material. But in our cases, we really care only about the number of unpaired d electrons. So we really care only about the electron spin. And if you do that, you can then relate mu of S directly to the number of unpaired electrons. And then this is called the spin-only magnetic moment. But S is actually just equal to, the spin. So if you have one unpaired electron, the S is then 1/2. If you have two, S is then equal to 1. If you have 3, S is equal to 1.5. And if you have 4, S will be equal to 2. And then finally, I have to write it up here. If you have 5 unpaired electrons, the value of S would be equal to 2.5. So we're basically attributing the spin of 1/2 to each of the unpaired electrons. And then that is called, obviously, the spin-only magnetic moment, but then that's related to effectively the theoretical values, which are here, to the experimental values. And we're really only concerned with the spin-only magnetic moment. We're not worried about anything related to coupling to the nuclei. So another way to do this, instead of worrying about doing spins, you can use N, and N is simply the number of unpaired electrons. And as you can see there, then the values of N would be 1, 2, 3, 4, or 5, because we're only concerned with really the number of unpaired electrons that are possible in the occupation of d orbitals. And then that allows you to quantify the spin, as you'll hear later in the chapter. High spin being synonymous with electron configurations that prefer to maximize the spin multiplicity. And then there's also low spin configurations where the opposite happens, where the configuration actually prefers to have the most spins paired as possible. And as you'll see, that's going to be related to these ligand field stabilization energies that you're going to see in octahedral geometries, tetrahedral geometries, square planar, all sorts of different geometries that we're going to come across. But as you'll recognize, high spin complexes have high values of the spin-only magnetic moment, and that's synonymous with small ligand field splittings in the d orbitals. And then low spin complexes are going to have small values of mu S, and then that's synonymous with large splittings in the ligand field stabilization energies, which we'll talk about in a later lecture. But to put it all together, this is really all that matters. So depending on which equation you prefer, you can write it in terms of N, which is just, again, that's just directly the number of unpaired electrons. You can use S, where you're basically using the total spin quantum number. And no matter how you shake it out, one unpaired electron gives you spin of 1/2, and that gives you a spin-only magnetic moment of 1.73. So I want you to recognize something here. Notice how if N is now 1, mu S of that is 1.73, and you'll see that the first integer of the spin-only magnetic moment actually matches the number of unpaired electrons. And then I want you to see, if you follow suit all the way down this chart, you'll see that there's the 2, there's the 3, there's the 4, there's the 5. So it follows all the way through. And like I said, we're not going to care about anything related to spin orbit coupling, so we're not going to really worry about what's in this column at all. But then, of course, if you have 2 unpaired electrons, the spin quantum number is 1. If you have 3 unpaired spins, spin quantum number is 3/2. If you have 4 unpaired spins, the spin quantum number is 2. And then if you have 5 unpaired electrons, the spin quantum number is 5/2. But again, recognizing exactly what happens is the number of unpaired electrons is actually scaling exactly with the spin-only magnetic moment. And really, that's all I wanted to cover as far as magnetic moments are concerned, because it's really going to be a diagnostic tool to figure out how many unpaired electrons there are going to be in transition metal complexes. And then as a result of knowing that, it can help us deduce what the actual real d orbital electronic structure in the molecule looks like. Okay, thank you, and I will talk to you next time.